Modern video generation models are incredibly powerful, capable of creating realistic-looking scenes. However, a critical flaw remains: they often violate fundamental laws of physics. Think about it: objects might suddenly teleport, accelerate unrealistically, or even disappear mid-air. This disconnect between visual realism and physical plausibility limits their application in domains like robotics simulation, scientific visualization, and even realistic entertainment. The core issue is that these models are trained primarily on visual data, lacking explicit constraints on physical laws. The key insight of post-training Newton's laws with verifiable rewards is that we can improve the physical realism of generated videos after the initial training, by rewarding behavior that adheres to Newtonian dynamics. Instead of relying on potentially noisy or biased human or VLM feedback, the authors propose using automated, physics-grounded metrics as verifiable rewards. This allows for scalable and consistent enforcement of physical laws. This approach is particularly impactful as it avoids the need to retrain the entire generative model from scratch. The NewtonRewards framework operates by first extracting relevant physical quantities from the generated video using pre-trained utility models. Specifically, optical flow estimates velocity and high-level appearance features from a frozen image model are used as a proxy for mass. These proxies feed into two reward functions: a Newtonian kinematic constraint, which penalizes deviations from constant acceleration motion, and a mass conservation reward, which penalizes changes in the object's estimated mass over time. The kinematic constraint uses optical flow and frame timestamps to estimate acceleration and then compares it against a theoretically plausible constant acceleration. The overall reward signal is then used to fine-tune the video generation model, encouraging it to produce videos that adhere to these physics-based constraints. Let's delve deeper into the Newtonian kinematic constraint. Imagine an object undergoing constant acceleration, like a ball thrown upwards. The framework calculates the velocity at different time steps using optical flow. Then, using basic kinematic equations like v equals u plus et, where v is final velocity, u is initial velocity, a is acceleration, and t is time, the framework calculates an expected acceleration. The reward is then inversely proportional to the difference between the estimated acceleration and a constant acceleration. This essentially penalizes videos where the object's acceleration changes erratically.